evening all. Wade here, VK1MIC. We're over at Dale's house tonight, VK1DSH. Him and Dimitris, VK2COW, will be starting the stream very shortly. But I wanted to thank everyone for joining our very first live stream. And we'll be kicking off at probably 8 o'clock on the knocker. So once again, please enjoy the hold music that we have playing, and we'll be back to you shortly. Cheers.
Good evening, ladies and gentlemen. Welcome to VK1DSH Shack, where we're going to experiment with a live streaming presentation. We have here Wade, VK1MIC, and Dimitris, VK2COW. And I want to thank the committee of the Canberra Region Amateur Radio Club for being forward-thinking and thinking this was a good idea and trying it out, because it's all new. So if it doesn't quite work properly, forgive us, but hopefully it will. Anyway, tonight we're going to talk about LoRa. I will start, and then Dimitri will continue. Then we'll take callbacks on the VK1RGI VHF repeater. So hold your questions until then if you can. Anyway, starting. So we're going to talk about LoRa. So what is LoRa? So it stands for long range modulation. It's produced by a company called Semtech. They own the patent. It's a proprietary spread spectrum protocol developed for Internet of Things devices, and I'm sure you've heard of that. That technology is increasingly being used for data acquisition, remote control and telemetry applications on all sorts of different things. Meter reading, control systems, all sorts of things. It's in wide use across the world. It typically uses ISM or lipid bands, somewhere between 150 megahertz and 1 gigahertz, depending upon the LoRa hardware chosen and the regulatory environment where it's applied. Since it's ISM or lipid use, it's license free, although what we're doing with it requires usage under amateur license conditions for reasons which you'll see soon. So why do we want to do this? Well, LoRa hardware is quite cheap, a few dollars a module, and it's reasonably easy to use. It can provide quite robust but usually short range radio links, and we thought it might be useful for radio amateur purposes. And it's certainly an experimental activity which is allowed under our license conditions. In fact, it's one of the important things that amateurs still do, is experiment. And LoRa is already used in a number of experiments for amateur work, typically high altitude balloons, and also applications similar to APRS. But let's have a look at some of the theory, which gives you an idea of why it might be useful. So there's a theorem called the Shannon-Hartley theorem, which lets us estimate what the maximum rate at which information can be transmitted in a bandwidth, given a certain signal-to-noise ratio. And the equation there is given as C, where C is the data rate in bits per second, is equal to B, that's the bandwidth, times log to the base 2 of 1 plus the signal-to-noise ratio. Noting that the signal-to-noise ratio there is a linear power ratio, not in decibels. If you assume that the signal-to-noise ratio is much less than 1, which isn't the way amateurs would normally work, that equation simplifies to something which is very simple, which says the data rate, C, is equal to bandwidth times the signal-to-noise ratio. And you can look all this up in the reference given. So assuming low power operation, which LoRa normally is, LoRa trades data rate for sensitivity within a fixed channel bandwidth. So a high sensitivity means a low data rate if bandwidth is fixed. But at UHF, bandwidth can be quite wide, hundreds of kilohertz if you like. So because of that, we can get a reasonable data rate, certainly a few kilobits per second with a bandwidth of 125 kilohertz. It's not a high speed mode, but it's quite sensitive and certainly more robust than FSK under the same conditions. So we thought it may have some use for amateur applications. How does it work? Well, it works by changing the start and stop frequency of a chirp. So for each byte, the frequency it starts and stops at varies within the fixed data range. And you can see in the spectrogram there, where the bit that starts with SFD, that the lines are broken. And so each line there each diagonal line represents a different byte. And the value of that byte is determined by the start and stop frequency. The preamble at the beginning is fixed, and that's required so that the receiver can synchronize to the transmitted signal. There are some restrictions on the data. Each packet can only be 256 bytes, but it's only a few hundred milliseconds long, and it sounds very much like a burst of static. So what do we want to do? Dimitri and I wanted to build a conversational keyboard-to-keyboard application using LoRa, something similar to RTTY or PSK31. We wanted to keep it cheap, simple, and reliable. Moreover, we wanted to have some fun and learn something new, and we thought LoRa was the way to do that. But there might be some issues to consider. Is LoRa allowed under our license conditions? Yes, provided we comply with those conditions, and the basic requirements are that there are limits on the spurious emissions, bandwidth and power. There'd be no encryption, so it'd be plain text, and we don't cause interference to other users. So if we comply with those obligations under our license conditions, we can use LoRa. However, spurious emissions was an interesting issue to deal with, so we'll look at that in a little bit of detail. There was some concern expressed by knowledgeable amateurs in our club about the level of spurious emissions from these LoRa modules. Our license conditions state that any spurious emissions must be at least 43 plus 10 times the log of the transmit power down on the carrier. And that is 57 dB with respect to the carrier in the case of a 25 watt transmitter. Note that this issue of spurious emissions probably isn't a problem if you operate the thing without an external amplifier, so operate it with just a few tens of milliwatts perhaps. Anyway, to understand the issue, we took some measurements to see how bad or good we were. This was done by using a 25 watt LoRa transmitter that I built and my IC9700 receiver, or the receiver part of my 9700 transceiver. Turns out that the signal meter, the S meter on the 9700 is extremely linear over at least an 80 decibel range. I could check that with a signal generator and a precision stepped attenuator, so I knew that the receiver was a suitable test device. So by sweeping across a range of frequencies, I could plot the response given by the receiver for the carrier plus any spurious emissions. And the chart there shows the peak at around about 432.8 megahertz, with the tails falling off on either side. The two vertical lines on the outer part, the red and the yellow lines, are the point at which the spurious domain starts, and that's 2.5 times the necessary bandwidth. And we had to be below the light blue line at about the 30 decibel mark. So if our emissions at that point were below the blue line, we complied with our license conditions. As it turns out, there are at least 10 dB down on that, so we comply with the license conditions. However, although it complies with the license conditions, the out-of-band domain, which is the space between the necessary bandwidth and the spurious domain, might be a problem in some cases. In our case, the VK1RGI inputs on 433.050 megahertz, and so potentially we have an issue if our LoRa transmits on 432.8. So there was some concern there, remaining concern. So what I did was check the outputs of 3 FT817 transceivers, looking at their spurious and out-of-band levels. The results are comparable, so if there was going to be any problems, I'm sure we would know about them now. So with those results, we felt comfortable and could proceed. What's more, we did some tests operating the LoRa transmitter simultaneously with usage of the repeater, and no problems were experienced, so we were quite comfortable then that we weren't going to cause any difficulties. So what have we built? Between Dimitri and myself, we've built a variety of units. I've built two devices, which you'll see shortly. A terminal, which is a full-featured terminal which provides beacon capability, conversational capability, all sorts of other things, and a test set which is really useful for developing the system. I used exclusively Arduino hardware, whereas Dimitri used a mixture of a Raspberry Pi and Arduino based hardware. We used the same LoRa protocol, and they all work happily together despite the different hardware and software. We operated at 432.8 megahertz, though it might be better if it became widely adopted to shift up to perhaps 444 megahertz, where we would cause no trouble at all. And we used the default configuration of 125 kilohertz with some other characteristics which is listed there. So the bandwidth's 125 kilohertz. We use a 4.5 forward error correction scheme and a spreading factor of 128. That was the option we selected. There are others, but that seemed to be the most reliable for what we wanted to do. These are my devices. I built two. The top one is the complete terminal. It's a standalone unit. It has a 25 watt amplifier and it works very nicely. Runs off 12 volts. You plug a terminal into it and an antenna and away it goes. You don't really need the heatsink, as I found. It's a very low duty cycle, so it doesn't get warm. So the heatsink is redundant. The lower unit's a 50 milliwatt device. It operates as a beacon and as a store and forward repeater, which is really useful for testing because you can have a conversation with yourself if you really want. And it uses an Arduino Uno. The top one uses an Arduino Mega. This is the insides of the terminal. You can see on the left hand side the Arduino Mega. Beside it's the LoRa module. There's a bandpass filter, some switching to RF relays. On the right hand side of the partition is the power amplifier module, a low pass filter and some more transmit receive relays. Quite straightforward, easy to build using no particularly difficult to get parts. I chose to have a menu driven operation. You can see a snapshot of the screen there. It gives you all the necessary information. You put in your call sign. It gives you a bit of information about the operation of the system. Obviously it hasn't got the battery connected with 1.66 volts. Normally that's 12 or 13 volts. You can set the operating frequency. It can operate at two power levels, high and low power. You can set the beacon interval, beacon text, and there's a whole lot of settings there that you can play with. And away you go. Ultimately the aim was to have a converse mode, so it can operate a bit like PSK31 or RTTY, and you can have a conversation using LoRa. The terminal system requires the Arduino Mega simply because the code is quite long and it wouldn't fit in an Uno, but the smaller test set happily runs on an Uno. The thing we did find was that the LoRa modules, the LoRa libraries in the Arduino aren't necessarily directly compatible, and I had to modify sections of the Radiohead RF library for us to overcome some difficulties we faced, which was a header information that was put into the packet which we didn't need and didn't want, and it puzzled us for a while why things weren't talking to one another, and I modified the library to remove that header and it all worked fine, and I'm happy to provide the source code to whoever would like it if they want to build something. So what have we achieved? Well, we've got working beacons. That was useful for testing the hardware and software. For a while I ran a beacon and drove around Canberra and got quite good coverage from my place at Flynn to Woden, certainly as good as the usual VHF repeaters. We did a one-way test between the ANU campus and Dimitri's place and my place, and that worked. Then we did a short distance QSO across the campus to confirm operation of the hardware and software. That was after we figured out that the headers were causing us troubles. Then, one miserable, rainy, horrible day, I went up to Dairy Farmers Hill with the Yagi and the set and worked Dimitri. Initially at 25 watts, but then Dimitris suggested we go to low power, and we achieved just perfect results of 50 milliwatts over a nearly 30-kilometre path, almost line of sight, and using short Yagas at either end. And it was just amazing how well it did work. Even at 50 milliwatts, we still had some 30 dB of margin on signal strength, so we could have done a much longer path. And I don't know whether it would have worked with 1200 baud AFSK on FM at 50 milliwatts, I don't know. But it certainly worked at LoRa, with using LoRa, so it shows great promise for reasonably long distance operation. So far we've concluded that LoRa hardware and software can be used for amateur purposes. We believe you don't need high power, just a few watts will give you reasonable results. Set up properly, it's an interesting keyboard mode, and certainly good to have a chat. It's easy to use. We could further develop it for mesh networks or forward and forward repeaters, etc. And one thing it may be useful for is for satellite telemetry, because it's thought to be quite tolerant of Doppler shift. And in fact, there are some satellites proposed to use it for telemetry downlinking. However, if you do plan to use it, you do need to consider compatibility with other applications in our bands because of the out-of-band emissions. So you don't want to be too close to other users because you may interfere with them. But if you're far enough away and low enough power, it's more than likely okay. There's some references there, and I'll hand over to Dimitri now. So hold your questions, and we'll answer them on the repeater in a little while. Okay, over to you, Dimitri. Over to you.
Hello everybody, my name is Dimitri, VK2COW, and I will say a few things about the more practical aspects of getting a little LoRa system together. That is the end of my presentation that I'm looking at right now. And that's the beginning. Right, so Dale covered the theory quite well, and of course he presented his beautifully made high power, really good LoRa system. I am usually operating at the other end. I want something quickly, and it has to be cheap because right now I'm a student, and that's budget is an important thing. So my presentation covers basically my investigation of all the modules you can get, usually from eBay, but there are other sources as well, and some of the software that you can get, and put everything together and make a little LoRa transmitter. So won't repeat what Dale mentioned earlier about the theory of operation for the LoRa modulation. All I'll say is that there are a few parameters that you need to know before you can communicate with some other LoRa system, and but we tend to use like one particular setting of 125 kilohertz, 4.5 coding rate, 128 spreading factor, and so on. So perhaps we don't want to worry too much about that. An important thing, as Dale mentioned, in order to comply with our license conditions, is to not use any encryption. And I found that, of course, there were some modules that you couldn't easily bypass that, and of course they are completely unsuitable for our application. Anyway, so with that objective, producing a keyboard-to-keyboard system that operates under the AR languages, I obtained a few modules and I start putting them together, and was very curious to see what is the biggest distance we can cover without spending too much money or using too much power, in the spirit of QRP. So one of the modules that came up a lot is actually no, sorry, I got the slides in a different order. The manufacturer that makes the LoRa products is called Semtech, and they have lots and lots of different modules. You can find modules that are really QRP. You can find modules that produce a bit more power. You have a choice in frequency, and I think that relates to which license-free or ISM band can be used. Even though none of this is an ISM band, I think. However, to our convenience, the 433 megahertz modules, which in Australia are meant to be operated under the Lipid class license, they're all very frequency agile, which means that we can shift the frequency outside the Lipid part, which is around 433, 434, and we can use them under our own license. They'll cover that pretty well. So the module that appeared quite often in my searches was something called SX1278. As you can see, it's like a little integrated circuit, a few dollars each, not particularly expensive. Produces 50 milliwatts, which may not sound like a lot of power. However, as Dale mentioned, we have had some really good success using just 50 milliwatts of power. Extremely frequency agile. I mean, this thing is VHF all the way to UHF, and I don't know how they managed to achieve such a huge bandwidth, but it works. I'm not quite sure what sort of. Obviously, you need to provide a decent low-pass filter if you want to use it on the lower frequencies. But anyway, it is possible. Technically, it covers both 2 meters and 70 centimeters. However, given the discussion that the problems with extremely high bandwidth that potentially could happen using these modules, I wouldn't suggest it's a good idea to use these modules on 2 meters. So one could buy one of these things and build a system together. However, that would require a little bit of SMD soldering and a few extra components, and probably, if you want to do it right, it would require building your own PCB, which is a lot of work. I don't want to do that. So keep looking was my attitude. So I found that there is another company, Chinese company, as you can see from the characters there, called AI Thinker, that produces, amongst other things, produces these two modules, RA01 and RA02, which basically is an SX1278 with a little bit of extra infrastructure around it. The RA02 has a little RF connector, so that makes life easier. It has 2 rows of pins, which are the standard 0.1 inch header pin connectors, so you can easily connect pins into that. So that was a much better option compared to the SX1278 on its own. However, you still need to do a little bit of soldering, and possibly even because really this is designed to be soldered on an SMD PCB. So I kept looking because it wasn't too hard to find a module that has all the pins that basically it's ready to connect to an Arduino directly without any extra stuff. Now these modules appeared on my searches in many different forms, and I obtained a few different ones just to compare and see which one is more practical and more convenient to use. Important thing is 3.3 volts versus 5 volts. I put that in there because the Arduino, which is the first system that I used it with, of course it's a 5 volt system, and you don't necessarily want to connect a 3.3 volt device on a 5 volt unit. However, there may be some workarounds you can do around that. For example, you can drive a 5 volt system with 3.3 volts. That tends to be okay. And on the other way around, putting 5 volts into a 3.3 volt system, generally you could put some series resistors, but maybe a bit risky, but it will work. Anyway, out of all these modules that I found that are based on the RA02 AI Thinker module, some were better than others. And here is a picture that shows the good one versus the bad one. Basically, the difference is that, as you can see from the top module here, you have a lot more pins available to you. These are SPI devices, and of course Arduinos are quite okay to connect to an SPI device. However, they have a few extra pins, and not all pins are available on the bad version of that module. So don't buy the one at the bottom, because you'll find there are some limitations. However, the top one is good. Alright, so that was the 50 milliwatt module. Of course, I thought maybe we can use a higher power version, because at the end of the day we are allowed to use more power as radio amateurs, and of course we are allowed to use high gain antennas too. So there's no real reason why we should limit ourselves to essentially the conditions of the lipid license that perhaps dictate that many milliwatts EIRP. We could go higher power. So I found this module here. This is by a company called eByte, and you can find this module in many different versions. There is like a 100 milliwatt version, 1 watt version, 5 watt versions. They have a built-in LNA, which is perhaps convenient for receiving. Again, because it is also an SX1278 module, all the software that works on the previous RA0102 modules will happily work on this one as well. However, there's one little difference, and that is that there are 2 extra I/O lines that are required. One is the TX enable and the other one is the RX enable. Of course, TX enable has to be high when you transmit, and RX enable has to be high when you receive. But that's not really a problem, because you have an Arduino, and your Arduino has lots of I/O and can easily cover all that. Again, similar story. It has a 0.1 inch header. You could attach something directly to it, and on the right side there is a little solder point for your RF connection. So that is good. That module worked quite well, and I have not done a full test of its spurious emissions. That remains to be checked, but so far, by having it connected on a dummy load, I was able to communicate with the other SX1278 modules, and that is a good sign. Both receive and transmit, which is good. Now, while looking on eBay, I found yet another thing, which is also made by the same company, eByte, and this appears to be a complete modem. So I said, oh, that's great, that's fantastic, because it's only about $40, and it's a complete unit. It has the one I bought has an RS-232, which directly implies you can connect it to your PC, and off you go. Looks really well built. In fact, it is well built. I didn't have any issues with its construction quality. It looked okay. However, it's not very good. So we have a number of issues with this module. First, it works on UHF only. It doesn't work on VHF. 410 to 441 megahertz. Okay, that covers the 70 centimeter band. However, you can only set the frequency in 1 megahertz steps, and as you can imagine, that is really bad if you want to be particularly good with complying with the band plan on 70 centimeters. It's not a good idea. But you might say, okay, that's not a huge problem. It is a very big annoyance. The biggest problem is that by default this unit is sending out encrypted stuff. Okay, that is a problem, and there was no obvious way how to disable the encryption. So straight away that does not comply with the LCD, so do not buy such a thing. Another little annoying feature that I discovered is that straight out of the box this unit is configured on 433 megahertz sharp, 433.0, and 250 kilohertz bandwidth, which of course is really bad, because our local repeater, VHF repeater on Mount Ginini, of course the input frequency is 433.05. So it would be really disastrous if lots of people that are not familiar with the spectrum licensing and so on obtain these modules and then we have trouble with Mount Ginini. But anyway, these things are available on eBay, and apparently they're very, very popular. So conclusion on this module: even though it looks really nice, don't buy this one. Now I want to quickly say a few things about the software, because again, one could just get from Semtech, get the SX1278 datasheet, and of course all the information you need to program it is there. However, lots of good work has been done by the Arduino community, and there is a bunch of different libraries that already have implemented all the features that you would like in communicating with such a module. And their code is available, it's free, and it comes with examples. So initially I started with something called LoRa by Santip Mistrip, and that worked well. Then I found LoRa Lib and Radio Lib, which worked even better. And when I was playing on the little Raspberry Pi, I found something called Radiohead, and that also worked. Out of all these modules, my favorite one is Radiolib, because the examples that it has, it comes with, are pretty good. It's well documented, well commented code, and it took me, I don't think it took me more than half an hour to modify one of the examples to produce the basic software to use it for a simple keyboard-to-keyboard communication. It was just adding a few extra lines of code to capture the text from my keyboard as I type it, and only send it out when I press enter. That's it. Straightforward. Now, an important thing to mention is the difference between LoRa and LoRa 1, the wide area network of LoRa. So we're not interested in LoRa 1 because that one is essentially has all sorts of extra information attached to the message in order to have the ability to provide a gateway service or a routing service, or things that we're not really interested in. We with Dale, we decided what we want is the simplest possible keyboard-to-keyboard communication system, where one person types something, presses enter, message is sent out, and the other person just receives it, and that's it. We didn't really want to look into routing and things like that. So that's why it was extremely important to have direct access to the system, and that's the reason why the module I mentioned earlier, the modem, is not suitable. There is a little ESP32 microcontroller that is connected to the other end of the serial port, and it's configured in a certain way, and there's nothing you can do about that. So, all right. So, and this is basically the ingredients for my first implementation. An Arduino Uno. Of course, it could be something else, but Arduino Uno was convenient and available. One of the good RA02 modules. A few connecting cables, and a little pigtail, because that RA02 has one of those really annoying tiny RF connectors that I have no idea how to terminate a cable with such a connector, but they're easy to get, those pigtails, and I got one, and that made life easy. So altogether, this system cost me a bit less than 25 Australian dollars, but now with the exchange ratio maybe a bit more, I don't really know, but it's not particularly expensive. And this is what it looks like in real life. So just a little die-cast box. In fact, it's a die-cast box that I salvaged out of a different project. The Arduino Uno is inside, the little module is floating over there, a little antenna, and USB to your computer. That's it, nothing else. Now, in the connection, which is this messy set of cables here, is quite straightforward. You have maybe 4 DIO pins which serve certain purposes, and library will allow you to change these numbers, these pin numbers, if you want to use them for something else. And the SPI signals, which on the Arduino Uno are available either on the in-circuit programming header or pins 10, 11 and 12, or in fact 11, No, I made a mistake on the slides. It should be 11, 12, and 13. So the actual connection is very straightforward. As mentioned before, we decided to stick to the default. I say default because it's not really default, but it seems to be a popular LoRa setting, which is 125 kilohertz, 4.5 coding rate, and 128 spreading factor. Then, of course, it was a question: what can you do with 50 milliwatts? Because unlike Dale's 30 dB more power, or not 30. 27 dB more power. It was a bit of a question: is this going to be useful or not? But Dale already gave you the results of these tests, and we were able to cover considerable distances, and it seems to with enough signal to noise ratio that perhaps indicates we can do better than that. Now, I didn't put a low-pass filter on this because I was able to test it with a little spectrum analyzer, and I noticed that at least the harmonics were well within the LCD specifications. So I have not connected a separate low-pass filter on this. A relatively safe experiment, because with 25 milliwatts or 50 milliwatts, so in fact I don't really know how much of that ends up going through this tiny little RF cable. It is not likely that you cause a lot of trouble. However, we always need to be aware of all these things, and that is very true for the higher power module, which I have not measured yet properly. I have only done tests on dummy load test. But anyway, other bonus of having such a simple low power test is that it gets powered directly from USB, so you don't need anything but exactly what I'm holding in my hands right now. That's it. Connect to the computer, and you get power from your computer. So that would be potentially quite convenient for a field operation. Now, that's my implementation of the 1 watt e-byte unit. As mentioned before, of course, that needs a lot more current at 5 volts compared to the so I couldn't power this directly from my computer's USB, so I put it on a little PCB, so you can see it on the slide as well. And it needs its separate power source. I had a spare Arduino Nano. I plugged that in. That's fine. And I just same pin out as the previous module that I showed you, the RA02, but 2 extra pins which are used for the TX enable and RX enable. Interestingly enough, the price of that module, the 1 watt module, was still in the order of $10 Australian. So it actually isn't more expensive than the other module, and as I said, it seems okay on the dummy load. We will test it eventually once we are certain that it complies with the conditions. We will test it on an antenna, and we'll see how it goes. Hopefully, from what we've seen so far, I think 1 watt is probably enough power to have all sorts of interesting QSOs using such a system. Now, as I hinted before, the software. My software is not particularly complicated. I just started with the example from the library, and I just added a few extra lines to capture the whole message from the user as a user types it, and only send it out when the user hits the enter key. I use RadioLib because, as mentioned before, that library was quite well written, and it works straight away. I didn't have any other comments. I mean, it worked surprisingly well. RadioLib supports lots of other LoRa modules that I have not tested, such as the RFM95, RFM96. There are a few other different modules, and I think probably you could use any of these LoRa modules, and you'll be happy. I just haven't tested them. Now, once you program your Arduino with your code, all you need to do is connect this to your computer. Then it appears as a serial device, and you can use either the Arduino serial monitor tool. That's convenient because it's available right in the Arduino IDE, or you can really use any serial terminal emulation system. And there are there's nothing that is configurable from the terminal. Whatever you type on your computer, it will be sent out. Little things that could improve could improve the system is perhaps to add your call sign at the beginning of each message or something like that, and that's not particularly difficult to implement. At this stage, the setting of the frequency is done at the compiling time, so it is hard coded in the code, but in most cases we have an agreed frequency and we don't care about that agility on the fly, frequency agility on the fly, so it's not a major disaster. And of course I'm very happy to share my code, which perhaps would be enough to get somebody started, and then they can produce a much nicer system. Some final thoughts. That was basically the intention of my contribution, that with an investment of a few dollars you can get a working LoRa system, low power, which is also safe in terms of QRM, and it is good to get some familiarity with the LoRa mode, because whether we like it or not, we'll see it more and more on the airwaves. This technology, as Dale mentioned, is an IoT technology, Internet of Things, which of course it is expected more and more devices will have that technology in them. So as radio amateurs, it's good to be aware of what's out there. Another comment, another final thought, is that the tiny little modem, this module here, which is the RA02, when I connected that to a full-size antenna, as in it was a vertical antenna with something like 5 dBi gain, something like that, it appeared to be desensitized, severely desensitized, as in I could hear this transmitter at my place in Gandaroo from the ANU, covering a distance of about 30 kilometers with 50 milliwatts. But when I did the opposite test, transmitting from Gandaroo and trying to receive at the ANU, there was absolutely nothing. And we also noticed that with Dale when we did some local tests. Perhaps a very strict bandpass filter will help, and given the proximity to the Telstra tower and the 50 kilowatt digital TV transmitter, perhaps that will be the solution for it, but that's yet to be tested. What else? Yeah, final conclusion is we can't really beat them, the IoT devices that are proliferating around the place, so I suggest we join them, make use and benefit from the super cheap, super fancy hardware that we can buy, and have some fun along the way. And that was my part of the presentation. I think now we are ready to take some questions on Mount Ginini, and I'll move out of the way, and
No problem.
Wade is going to take over.
Hello again, everyone. Thanks again for joining in our stream tonight. We've been interesting seeing the technology work. This is the first time we've got it to work with us, and obviously we've got Dale's shack as a wonderful backdrop tonight. So I wanted to thank Dale and Dimitri for their presentation tonight. I'm going to end the stream on Facebook now, and I'll make this video available as an offline version, available on our YouTube page. I'll also be sharing the PDFs of the slides, and we've had a request by Facebook for access to Dale and Dimitri's code that they had on their chips. So if they are forthcoming, I will definitely be sharing those. So I really want to thank everyone for joining us tonight and bearing with us for any glitches you experienced. And so we'll be taking questions on the repeater that's currently on screen. And I'll end the stream here, and I'll leave it to the experts and not me. So once again, thank you for joining us, and I really hope you enjoyed our stream this evening. Cheers.